In the left is the picture of a town. In the right is the graph representing the road structure of that town. I would like to build a fire station for this town. Where should I put the fire station? I want to build a police station. Where should I put the police station? I want to build a water company. Where do I build the water company, power company, to minimize the amount of pipe needed, to minimize the amount of wiring I need to run? For the fire department or the police department, to minimize my response time. Where do I put these things? All right. If I wasn't thinking about a graph, but just thinking geographically, my brain says put it in the middle of town, right? Thus, center. So the big question of the day is, how do I find the center of a graph? I mean, at this point in time, police cars don't fly. Neither do fire trucks. So they have to drive the roads to get to all those other houses. So I want to minimize the driving roads, the distances. I want to minimize what I can. Okay. Distance. Graph distances. I'm back to chapter 1. Given two vertices in a graph, the distance, DUV, is length of the shortest path from U to V. What do we call such a shortest path? A geodesic. In a connected graph, this makes sense for every pair of vertices. In a disconnected graph, vertices in different components can be defined to be an infinite distance apart or to have an undefined distance. And when we were doing things like the edge weights, we said if there was no connection, we could put infinity or we could put a dash. Same idea here. If U and V are in different components, we can say their distance is infinite. What do you know about the distances? What are the properties of this? I'm back in chapter 1. And this is like page, 14, 15, somewhere in that beginning part of the book. As a function on vertices, what do we know? Why would it be between 1 and -1? What's n? Unfortunately, the answer to that comment is no, because I could ask for the distance from U to itself. How far is it from here to here? At this point, I'm not going to worry about an upper bound on the distance. I'm just going to say it's definitely bounded below by 0. And it's only equal to 0 at a vertex to itself. But what else do I know? Again, these are properties we discussed earlier in this semester, but we discussed them in lots of other courses, like discussing relations in discrete and abstract and lots of other courses you've taken with me. Distance from U to V compared to the distance from V to U. Why? I hope so, but why? Because this is not a digraph. In a digraph, we had that D with the arrow over it, we had directed distance, and then it might not be the same. But this is an undirected, a simple graph. If I can get there, I can get back across the same road. That's the same length, whether I'm going from U to V or V to U. So it's symmetric. Not reflexive, because I'm not talking about relation in this sense. But transitive still comes into play here, right? I go from point A to point B and then from point B to point C, right? Geometry time. The distance from point A to point B plus the distance from point B to point C is not always. The answer is not an equal sign, unfortunately. At least that one is bigger, right? Because the shortest distance is to go directly. If you go, it might be the same, but it might be bigger. Which makes a picture out of A, B, and C that looks like a triangle. Guess what we call this one? That one was symmetry. This is called the triangle inequality. Where have I heard that before? Vectors, anybody? Now, Abigail, if I have a geodesic and a BC geodesic, and there is no other way to get from A to C except to go through B, then this will be equal. But there might be a shorter path. With these four properties, sometimes 1 and 2 get combined, we can actually refer to the distance as a metric. And then the set of vertices along with this distance function is called a metric space. Now, that's really a concept from topology and analysis, and it's the overall general theory of metrics is beyond the scope of this course. But there's a lot of very interesting ways to measure distances that aren't necessarily about how far apart things are physically. The one that I use most often actually has nothing to do with physical objects. I talked about this in linear. Some of you have heard this story before, but I want you to consider the set of objects. Now you get on your internet radio app and you feed it a song, right? And it feeds you other songs. How does it know what song should be next? A list of criteria. As a matter of fact, Pandora uses 450 some odd criteria, and they make a 450 dimensional vector out of a song. And then you measure how far apart songs are with a metric. And the song it feeds you next is close. I don't know. What's epsilon? Well, what it actually does is it feeds you a song and you either thumb up or thumb down, and then it keeps going in that direction. If you say, no, it goes the other way, because we have direction and we have distance in our metric space. Music. All right. I want to do this on a graph, so I'm going to have the universe of vertices and this distance idea, and then I say to myself, all right, what do I really want to know about my town? Figure out where to put the fire station. I want to know how far away things are. I'm going to define the eccentricity of a vertex. For any vertex in my vertex set, E of V, the eccentricity of the vertex V, is the distance from V to the furthest thing in G. If I were allowing really infinite graphs, I would talk about the supremum of this set rather than the maximum. But since my vertex set is finite, there is a maximum in it. If we have disconnected graphs, that maximum could be infinity. Why, for the moment, we're dealing with connected graphs. Okay. The smallest eccentricity is called the radius of G. Now, remember, that's the smallest, largest distance. So, what's the biggest, largest distance? The maximum of my eccentricities is the diameter of my graph. So every graph, every vertex in the graph gets an eccentricity. I can find the smallest one, find the biggest one. Now, that might not be unique, right? This number is going to be unique, but it may occur on several vertices. If the smallest distance from vertex A to other things is 3, the largest distance, the eccentricity of vertex A is 3, and the eccentricity of vertex B is also 3, that's okay. But that's the smallest one, or the largest one, respectively. Any vertex whose eccentricity is the minimum is called a central vertex. The subgraph of these vertices is the center of my graph. It is possible for every vertex to be central, in which case we say that the graph is self-centered. Here's a graph. I would like to find the eccentricity of every vertex so that I can find the center. So pick a vertex. Say again? E. Find the distance from here to the things furthest away. I think it's probably easier to find the distance from here to everything, right? So D, E, C, and F are all distance 1. That makes B and G distance 2. And that makes A distance 3, right? So the eccentricity of this vertex is 3. The furthest possible distance away. Keep going. Pick another vertex. G, start measuring. B and F are 1 unit away. A, C, and E are 2 units away. And D is 3 units away. So the eccentricity here is also 3. I need 5 more. Say again? Not quite. What was that, Cole? D would be 4, Lauren. C is 2, and B is 3. Well, let's count our way out, right? From here, these are all 1, 2, 2, 2. So anything coming out from C takes 2 steps to get to. What's the center of this graph? I'm calling this graph H because we use G as a vertex. It's not just C. It's the subgroup induced by all vertices of lowest eccentricity. It's FC. Now, I deliberately did this example because I stole it from a different book. That one's not in our book. But in our book, we have this picture. And they've already laid out all the eccentricities. And so we see the center are those 2 black labeled vertices over there, both with eccentricity 2. Yes, sir. That's a good question. I don't know. I don't have an explicit answer for that off the top of my head. I'd like to find out. I don't know. We'll have to find out. Literally, I have no idea. Other questions? Don't know why the screen is so pixelated right now. It's particularly fuzzy to me. It would be really nice if radius and diameter behaved here the same way they do in circles. What's the relationship between radius and diameter? Would be lovely, wouldn't it? I would like the eccentricity of every vertex in that graph. For all of them. Wait a minute. The radius is the smallest eccentricity. Radius of that graph is 2. The diameter is the largest eccentricity. The diameter is 2. Well, shit. Please label each vertex with its eccentricity. Three. So the radius is 2 and the diameter is 3. If I add another wing to this graph, over here, the radius of that graph is 2. Because the eccentricity here is 2. But what's the eccentricity here? It would have been so nice. No, the radius is not only not half the diameter, it could be the same as the diameter, or half the diameter. On the other hand, I can get close. The radius is not half the diameter, but the diameter is between the radius and twice the radius. All right. Sure it is. Why is that true? Well, the left inequality, I hope, is obvious. Why do I know the radius is smaller than the diameter? And the diameter is? If the smallest and the largest are the same damn thing, the radius better be smaller, the minimum better be smaller than the maximum. Why do I know the diameter is less than or equal to twice the radius? Because we're in a metric space. I have the triangle inequality. I want to know the shortest distance from point A to point C. Right? But instead of a starting distance from A to C, let's start at a vertex in the center. There has to be at least one vertex whose eccentricity is the radius, right? Well, then call that one B. From A to B, radius. From B to C, radius. So from A to C is never more than twice the radius. Triangle inequality. Son of a. So it turns out being a metric allows me to say that. Now, I will point out that in the graph we see, I did not compute all of the other eccentricities. What's eccentricity over here? symmetry, right? Why must two remaining eccentricities I haven't actually computed them by hand. I haven't counted. Makes sense, though. It should be 3, right? If I'm on the left side, I got to go all the way over to the right. If I'm on the right side, I got to go all the way over to the left. I don't have to go further back, so there's one less step to take. Why? If my two vertices are adjacent, why must the eccentricities differ by at most 1? I want to write this one out because y'all are staring at me like I'm a space alien. Only thing I know about U and V is they're next to each other. So let's pick one of them. The way I've written EU minus EV. I'm going to make the assumption that EU is the bigger at best. Without loss of generality, assume E of V is less than or equal to E of U. That way I can ignore the absolute value sign. All right. There is some vertex furthest away from you. Yes? Well, that means I know what the distance between U and X is. It's the eccentricity of U. That's the definition. It's one of the vertices that is as far away as I can make it. But U and V are adjacent, right? By the triangle inequality, instead of going straight from U to X, if I go to V first, that's bigger. What's that number? That's a distance. What number is that distance? U and V are adjacent. Wait a minute. The distance from V to X, I don't know if V is the furthest thing away from X or not, right? But that means that that's less than or equal to 1 plus E of V. Because E of V is the farthest distance you can get from V. And this X might not be far away. It might be closer. EU less than or equal to 1 plus E of V. Ta-da! Triangle inequality rides to the rescue again, damn it. By the way, if it's true for the eccentricities, it's true for the distances too, isn't it? Ignore the fact that I wrote E of U there and E of V here and just use the middle three sentences. Questions? In both my example and in the example of the book, our center was a path. 2 vertices, 1 edge. So I could ask the question, is that always true? What kinds of graphs can be centers? Turns out the answer to that is anything. No, it's not always true that the center is a path. Any connected graph can be the center of a connected graph. And that means that any graph disconnected can be the center of some other graph. So there's my answer. It is possible for the center to not be connected. Only if the graph itself is already disconnected. So within a connected graph, my center is a connected item, not necessarily in any graph. But any graph G can be the center of some other graph H. Sure. Well, what I do is I build a new graph. And I build the new graph by adding it to some other vertices, right? So I have some graph with a set of edges and a set of vertices, and I am going to create a new graph, H. The vertices of H are all of the vertices of G and 4 more, U, V, U1, V1. The edges of H are all the edges in G and an edge from U to every vertex of G, that's why it's GI, a edge from V to every vertex of G, and two more edges, U to UI1 and V to V1. Best part. Eccentricity of U1 is 4, so is the eccentricity of V1. Because to get from V1 to any other part of the graph, I have to go from V1 to V, from V to GI, from GI to U, and then from U to U1. So U1 and V1 are furthest apart from each other. The difference between adjacent vertices is never more than 1. U and V are closer in. We go down by 1. But then every vertex in G is at most 2 apart. You either go through an edge that's already in G, or you go G to U, U to G. Hey, wait a minute. These are all vertices from the original graph G. G is the center of my graph H. Whew. Can I get a disconnected center? Start with any disconnected graph, add 4 vertices and connect like this. And then your center is the graph you started with. So that answers my question, although I didn't realize it at the time. Here we go. If my graph was connected, where would I find the center? Because really, that's where I want to build the fire station. That's where I want to build the police station. What do I need to avoid? And if it avoids a bridge, then it avoids the vertex on each edge of a bridge, a cut vertex. So if I take my graph and I take it apart at the cut vertices, what do I have? Blocks. My center has to be in a block to avoid going over a bridge. Exactly right. If I want to make my life easier, I should never have a bridge that is required to be crossed. Problem. What do you know about this graph? Sorry again? No, because there's a vertex of degree 3 right there. Probably Hamiltonian, but I'm not sure that matters either. It is bridgeless. It's also definitely not going to contain any cut vertices. That's got to be at least 2 to disconnect. If it turns out to be Hamiltonian, right? It's going to be at least 2 to disconnect. Might be more connectivity, right? I don't know. So if I want to know back in this town, where do I put the police station? Where do I put the fire station? I actually need to do the hard work and figure out the eccentricity of every single vertex in this graph. Then I find the center of the graph. That's where you should put the fire station. And if you don't want to build one dense cop block, put the police station on a different in the center. But then you know it's no more than 5 roads. 5 stoplights you've got to interrupt. Sorry, 4 stoplights to get any other spot on this graph. You found the most central location. I want to take this outside of the application we were just dealing with. Where's my data center go to lower the lag time for requests for records? How many computer nodes are between me and that data server? If I want redundant servers, they should all be in that center. If I can build closer, if there's a more central location, can I get there? A trader in New York built a data center 2 blocks closer to the stock exchange. Shaved 5 nanoseconds off their trading time. Made in 1 month over $1 billion. Faster data. It's a useless idea. They made $1 billion moving the center of the graph. We have more to talk about this idea, and that is what we will do on Friday. See you then.